This is the screencast for Chapter 25 homework. We've seen the we've seen the conceptual questions already and gone over those in class. So I'm going to go over those pretty quick. Just scan through them. The problems like so. So we'll go over those. For problem 2, figure out the voltage across the moving wire in the magnetic field. It's simply equal to E equals B times L times V. So that is the potential difference across that moving length of wire. For number 4, we've got a rod which is moving, and the rest of this loop is fixed. And so, it ends up basically changing the area. So you could think of that as a couple ways, either change in flux over change in time, or again, you could use BLV. To find the current through the loop, you need I equals V over R. In this case, it's EMF over R. So you need to find the EMF first. The rod had a resistance of 0.65 ohms. So that's what would go in the resistance part here. So for the BLV, again, we plug in the quantities that are known. This current, by the way, would go clockwise because the flux is decreasing, and therefore you're going to induce a current and induce a magnetic flux inside the loop that will oppose that decrease. So you would have X's inside of the loop, and that would result in a clockwise current. So we get a potential difference of 0.735 volts from one end of the wire to the other end of the, or from one end of the rod to the other end of the rod. And then to figure out the force to keep it moving, we could simply use this formula which we talked about earlier, B times I times L. So 0.24 newtons would be needed for that. For problem 4, oh, that's a funny post-it. For problem 10, yep, it is 10. We've got two areas here, one with magnetic field coming out of the page, one going into the page. Essentially, the net flux would be 1 Tesla times this area, which is 0.2 times 0.2 meters. So it's 0.04 meters squared. So that's 0.04 Webers, and that would be into the page is the net flux. For P15, we're going to use this version to find EMF. So it's change in flux over change in time. So that's delta BA over delta T. So in this particular case, again, the flux says goes from, I think, either 0 to 0.1 or 0.1 to 0. It doesn't matter because we're not asked about a direction. So it's just that the magnitude of change is 0.1 Tesla in 0.01 or 1/100th of a second. The area is pi r squared of that loop. So pi times 0.01 squared because it said that the diameter was 0.02 meters. So when you do that, I get like 0.00314 volts. But there's 1,000 turns. So 1,000 turns means that that voltage would be built up to 1,000 times that amount. So that's 3.14 volts. I'll demonstrate something like that with the Tesla coil in class. It is a shocking demonstration. Okay, so for number 17, you've got a resistance of 0.1 ohms, diameter of 10 centimeters for a loop like this, and it tells you that the rate at which the field is increasing or decreasing. And you're asked to find the current in that case, so you really need to find the EMF. So first of all, we're going to get the area, which is pi r squared, so that's 0.05 meters squared. So you have an area of 7.85 times 10 to the negative 3 square meters. So to find out the EMF, we have change in flux over change in time. So the field strength is changing at 0.5 Tesla per second, and then the area is what we figured out earlier. So that comes to 0.0039 volts, divided by the current is 0.039 amps, and that would be clockwise based on what we see here. This one would be clockwise also, because a decrease in flux into the page has the same effect as an increase in flux out of the page. Those would both be opposed by having an increase in X's or an increase in flux into the page within these loops. This one, because this loop is parallel to this magnetic field, has no change in flux because there's no effective area. For the last two, or the next two, 20 and 21, it was shown that you had an 8 by 8 centimeter square area, 150 milliamps, resistance of 0.1 ohms. So if the current is counterclockwise, that says that to induce more X's in here, or for counterclockwise rather, that would be dots inside here, which essentially would oppose an increase in X's. So it says that that magnetic field strength is increasing. We can figure out the EMF from Ohm's law, I times R. So 150 milliamps is 0.15 amps, 0.10 ohms, that's 0.015 volts. So we should recognize at this point that that's equal to the rate of change in flux per time. Well, that's going to be the field strength change per time multiplied by the area. Actually, I wrote that wrong. It should be delta B or delta T. I will fix that thanks to the miracle of editing. There, no one will know. So the area is 0.0064 square meters. Get that, and that's equal to 0.015 volts times that change in flux. I'm going to do that again because I screwed up twice. And so that's, I believe it was 2.34 Tesla per second. I'm going to put it down there. Okay, for number 21, again, it's 20 centimeter by 20 centimeter area, 20 ohm resistor, 9 volts here. So we get the area for that. Time intervals, again, 10 milliseconds or 0.01 seconds. The change in flux is 0.5 Tesla. So I can get that the EMF here, 0.5 Tesla over 0.1 seconds times that area is 2.0 volts. But now the key thing here is if I need to find out whether that 2 volts is helping the 9 volts or hurting the 9 volts. So I initially screwed up with how I thought about that. It's actually helping the 9 volts because of how this is changing. So essentially, that voltage is going to be pushing a current clockwise. That means that I would be having X's inside of the page or inside of this area. That's because the flux is increasing and those X's oppose the increase in those dots. And again, please on the AP exam don't use dots and X's, but get an idea of that. So basically that 2 extra volts means that we'd have a net 11 volts divided by 20 ohms, and that's 0.55 amps. Last one here is pretty complicated. I'll talk about this in class. I'm sure we'll go over it. But it's actually really interesting because it relates back to mechanical things. So 10 centimeter area, this is very similar to some of the active physics problems. So it's asking to find the pushing force. So what I'll do first is find the induced voltage and current. So that's BLV, done that before, 0.025 volts divided by 2 ohms, that's 0.0125 amps. And now I can actually use this formula to figure out the force. So that's 6.25 times 10 to the negative 4th newtons. So this force would actually be to the left, and therefore the pushing force would need to be to the right to keep this at a constant speed. So the next thing was asked to figure out power. Power is equal to force times velocity. Why? Because power is also equal to work divided by time, or work per unit time, and that's force times distance over time. Well, that's what force times velocity is. So that gets me that amount of watts, 3.1 times 10 to the negative 4th watts. The current is counterclockwise because the flux is decreasing since the area is decreasing. So therefore, we're trying to oppose that. That would, again, be a counterclockwise current. We already figured out that amount. For part D, the electrical energy dissipated is equal to either V times I or I squared times R. It doesn't matter how you figure that out, it will be the same. So 0.02125 squared times 2, or it would be 0.0125 times the voltage we found earlier. Hey, I'm going to remind you later. So in this case, we get a also 3.125 times 10 to the negative fourth watts. So these should be the same because the power given by the force causing that wire to move should be equal to the power that's dissipated in the circuit. So that says that the mechanical work done per time is equal to the electrical work done per time. Hopefully those make sense. Hopefully you got at least a decent chunk of them correct.